basically, this talk will be on the background of gravitational wave sources. And due to that, I will explain a lot of astrophysics to you in a very simplified way. Now, first of all, I should mention that the work that is I'm going to describe towards the end of the talk is jointly with my colleague, Professor Linjing Wen. She is a professor of physics at my university. Her student, Manoj. Joyun is a student of both Linjing and me. That is, we supervise him in his PhD jointly. And Kevin is a radio astronomer. So we are a diverse group of people. I am a computer scientist. I am not a physicist. So we are a diverse group of people who did this work. But let me first show you the outline of the talk. I don't assume any background from you. I'll first explain. I thought about the ordering of these topics quite a lot and couldn't come up with a good ordering. So I decided that I'll first explain to you how gravitational waves are detected. I'll briefly tell you how it is generated, but we'll come to that in much more details later. So first I'll explain how gravitational waves are detected, then how gravitational waves are created or generated, why gravitational waves are important, because a lot of people are researching gravitational waves, so why it is so important, and moreover, why is it important to localize the sources. Now, this is a peculiar problem that doesn't happen in other areas of astronomy. If you want to observe a star, you can direct your telescope to the star and see what is going on. But even though we can detect gravitational waves, we don't know from where it is coming. It is coming from somewhere, and it is very important to know where it is coming from. And at the very end, I'll explain to you what we have done for localizing gravitational wave sources. Okay, everyone knows from school that what is gravity, and all of you have studied this equation, Gmm by r square. This is Newtonian gravity. In Newtonian gravity, the influence of gravity propagates at infinite speed. So if I put a star somewhere in the universe, the whole universe instantaneously knows the effect of that star according to this equation. But Einstein later modified or improved that picture, and according to the general theory of relativity, by the way, I'll not do any maths in this talk. It will be without mathematics. Only I'll show some formulas towards the end, but that's not very important. So, in general theory of relativity, gravity propagates through gravitational field, unlike in Newtonian gravity, where gravity propagates action at a distance, as you know, according to this formula. Now, what is a field? Any mass creates curvature in space-time. This picture is not particularly good, but everyone shows this picture, that whenever there is a massive object anywhere in the universe, something like this, let us say this is our sun, the space-time around that object gets curved. So, in effect, actually, Earth or other planets like Mars or Jupiter, they are trying to move in straight line. But due to the presence of the sun, the space-time around the sun has become curved, and the shortest distance between 2 points is actually an elliptical orbit. And that is why the planets move in that elliptical orbit. As I said, it's not a very good picture because we are trying to show a 4-dimensional space-time, because 3 space dimensions, as you know, x, y, and z coordinates, Those are the three space dimensions, and also there is time. In relativity, space-time is mentioned together or used together. But we are trying to illustrate that by giving a two-dimensional picture, or let's say three-dimensional picture, which is not good. But anyway, you got the picture that because the effect of gravity propagates through curvature of space-time, the curvature takes time to propagate. So if I put a star somewhere in the sky, that effect will propagate because the curvature of space-time will propagate over time at the speed of light. And it will affect other objects somewhere else in the universe. Okay, so these are the things I was mentioning to you. And if you read history, and I'm sure some of you at least will study general theory of relativity, you'll see that there are certain effects which are impossible to explain using Newton's mechanics, which Einstein could explain through general theory of relativity. And also one of the great tests of curvature of space-time was confirmed in 1920. Einstein actually gave this theory in 1916, and in 1920 there was a total solar eclipse. That means the moon covers the sun entirely, and it was possible to see the light from stars which are behind sun. How is that possible? Because the sun should block that light from a star that is behind it with respect to us. It was possible because due to the presence of the sun, the space-time was curved, and the light came shortest path, but the shortest path itself was curved, and it simply bent around the sun and reached the telescopes on Earth. So that was a great confirmation of Einstein's theory. Okay, so for our talk today, we'll see that two massive objects rotating around each other create gravitational waves. For the time being, we'll be happy with that, but I'll explain to you in more details what kind of objects they are and how they create gravitational wave. So here is a picture of two massive objects. As you can see, those two black things going around each other, and that is creating a ripple that propagates through space-time. Now, this is not like you're throwing a stone in a pond. There is no medium. We know that water waves propagate through the oscillation of water particles. They oscillate vertically, and the wave propagates horizontally at 90 degrees. But here there is no medium. The space-time itself is oscillating. That means it is contracting and expanding. Now this is a very strange thing. That means if a gravitational wave is passing through this seminar room right now, most probably it is passing through, then this thing in my hand, its length is periodically increasing and decreasing. Because whenever space contracts, then everything in that space also contracts. And whenever space expands, everything in that space expands. So wherever gravitational wave passes through, the space itself contracts and space itself expands. And since these objects are in the space, their length will increase and their length will decrease periodically, because it is a wave. As you can see here, it is just rippling through. Now, this is very strange compared to what you know. It is not strange because it doesn't require any medium, because if you have studied electromagnetism, you know that electromagnetic waves also, they don't require any medium. That is why we can see light from stars, because between the star and us, there is vacuum, almost vacuum, and light can propagate through that. That is not the strange part. The strange part is that whenever gravitational wave propagates, it contracts the space itself. That is, anything in that space will contract and expand. The lengths will differ. And we'll use this idea for detecting gravitational waves, or people are using this idea for detecting gravitational waves. The strange thing is, though Einstein predicted gravitational waves, the theory is very long. You have to first study general theory of relativity, and Einstein introduced the notion of linearized gravity. That means the field equations of general relativity are nonlinear. If we make approximation, then we can arrive at a wave equation. Now, Einstein predicted it, but he never believed it. Never believed in the sense that he never believed this thing will be detected. But it was detected first time in 2015, and if you keep track of things, then you will know that I think in 2018 or 17, 3 people got Nobel Prize for that. Okay, so our aim right now is to understand how gravitational waves are detected. You can see this is a gravitational wave telescope, this huge thing. Each part is 4 kilometers long. You cannot see the entire length. There are 2 arms which are at right angles. There are 2 telescopes like that in, I'll show the names of the places, 2 in the United States, 1 in Italy, that is called Virgo. LIGO is the name of the telescopes in United States. And also there is in Japan, just now, in the last few months, 1 new telescope called Gagra, and there will be 1 in India by 2024. I don't know the exact location. That will be the 5th gravitational wave telescope in the world. We'll see why we need so many telescopes. There are reasons for that. So if you have studied optics in your undergraduate curriculum, you must have read about interference of light. Now, since light behaves both as a wave and a particle, due to the wave nature of light, depending on whether there is a phase difference between 2 different lights, 2 different light sources, then if there is a phase difference between them, then they interfere with each other due to destructive interference. That means if one light source is producing a crest and another is producing a trough, both of them cancel each other and net result is 0. And that is why you get so-called interference fringes on a screen if you have 2 light sources which are out of phase. Or if you have 2 light sources which are in phase, then they enhance each other because their amplitudes add up and you get a brighter light source. So that is the idea of gravitational wave detection. Let's see how it works. The full form of LIGO is Laser Interferometer Gravitational Wave Observatory. There are 2 observatories. One is Livingstone in Louisiana and one in Hanford in Washington. Each of these devices, the other ones are also the same. In fact, the one that will be built in India will be also exactly the same. Each device is a Michelson interferometer. That means we produce 2 different light sources, and when nothing is happening, then those 2 light sources are exactly out of phase and they cancel each other and we get a dark patch. But when a gravitational wave is passing through that device, then as we have seen that due to the passage of the gravitational wave, everything contracts and expands periodically. And that is why the length of those arms here these arms will contract and expand periodically. So what will happen is the length of the path that the light is propagating through will be periodically shorter and longer. And that will create interference fringes. And we detect the interference fringes and try to find out who is producing those fringes or what kind of source is producing. I'll show you a video I have taken from LIGO website actually. But this is the last point here. In normal circumstances, the two beams are out of phase and those two beams cause destructive interference. But when gravitational waves pass, then they will create periodically destructive and additive interference, constructive interference. Mention another thing, that even though the arms of those interferometer, they are 4 kilometers long, actually the length is enhanced or increased by periodically reflecting the laser beams. Light here is laser because as you know, normal light, like the lights over here, they have many different frequencies in them. White light you can break up into red, green, yellow, etc. But laser light can be produced which has a single frequency. So that is very important. So these are laser sources. So the two beams are reflected back and forth about 100 times to increase the sensitivity. The longer the arms, the sensitivity will be better, but we cannot build a 400 kilometer long interferometer. That will be very expensive and very hard to build. So to simulate that effect, the beams are reflected back and forth many times. So as I said, when a gravitational wave passes, the two arms are squeezed alternatively, causing the changes in length and changes in the interference pattern. And I'll show you in a minute how that change is captured and how that is used as the signal for gravitational wave. Okay, so how much? I told you that if a gravitational wave passes through, the length of this thing will change. Now you may ask how much it will change, because surely it doesn't change 1 centimeter or something like that, then we would have noticed by now. Actually, the change is very, very tiny. The sensitivity is less than 10,000th of the diameter of a proton. So the change in length, in particular, if the source of the gravitational wave is far away, as you know, any effect dies down or the strength of the effect reduces as you go from further and further from the source. The sources that have been detected, they are billions of light years away. So a source from that much distance will cause a change in the length of the arm of the interferometer by about 1 by 10,000 of the diameter of the proton. You can see how absurd that size is. And that is why Einstein never believed that anyone will ever detect gravitational waves. But we can do it now. That is the nice thing. So I'll show you this video. At this stage, you can see that this is the laser source, and there is a laser beam coming out of it. This thing here is called a beam splitter. That means it allows half of the light to go through it, and half of the light is reflected. Now, here is a mirror. These are the two arms of LIGO. Okay, one arm is like this, one arm is like that. These are the mirrors. The laser light actually goes, I have shown you the simple picture. The reflecting back and forth is not here, but the laser light goes and reflects from here and goes and reflects from there. If there is nothing happening, then these two lights, due to the beam splitter, are out of phase or in opposite phase. So what happens then is when the light from here and here gets reflected and comes here, they will destructively interfere with each other and we'll see nothing. So that's what is happening here. Now you can see the same picture in terms of waves. If you think of light as a wave, then it goes and gets reflected from that mirror. Similarly, it gets reflected from this mirror, and both of them come here. And as you can see, they are in opposite phase. If this light is up, the other light is down, and they cancel each other. So you get a black spot. Now, what happens when gravitational wave is passing? As you can see, this mirror and that mirror, they are oscillating. That means the space is contracting and expanding. And periodically, the two waves will be in phase and out of phase. So what you'll see here, a periodic intensity of the light and a black spot, light and a black spot. In other words, you will see an oscillating nature of the pattern of the signal. So we have seen this one, and as a result of the change in intensity due to destructive and constructive interference, you see a pattern like this. The intensity is increasing, decreasing, increasing, decreasing, and eventually there will be a rapid increase and decrease. So this is your gravitational wave, and this is the signal we want to detect. However, experimental physics is not that simple. One of the things that makes our life miserable is this blue thing. The blue thing is called the noise. That means even though there is a gravitational wave signal, it is inside a lot of noise due to different reasons. I'll show you some of the reasons why this noise is created. So actually what you see in your instrument is these blue things. And inside this blue thing, this nice gravitational wave signal is hidden. So somehow you have to bring it out and you have to analyze it. That is the difficult part. Why so much noise? Actually, detecting gravitational wave is mainly engineering and signal processing. Once you have set up the detector, once you know how they are produced, then what you do after that, you analyze by computer, whatever you are getting. The problem is, for real gravitational wave, the signal to noise ratio about 10. That means the strength or the power of the signal is at the most 10 times the power of the noise. And how noise is created? Sources of noise is low-level seismic activity, bhumikampo. Even though we hear about earthquakes only when they are very large, actually earthquakes are happening all the time, 24 hours a day, at a very low level. And this instrument is so sensitive that it picks up all those earthquakes. Because if earthquakes are happening, then that shakes the mirrors at the end of the two arms. And shaking the mirror has the same effect as contracting the arm or expanding the arm. So it picks up that kind of signal. Now there are even wind. If there is heavy wind, even though you can say that a pipe of the interferometer arm, which is set on concrete, nothing happens there. But we are talking about movements of the order of the size of a proton or an atom. So even the slightest or medium level wind can affect the or vibrate the mirrors. Then there are blip transients. People in gravitational wave research, they call them glitch. How does that happen? Even if there is a truck going, let us say 100 kilometers from the detector, and a very heavy truck, this detector will pick that up. So suddenly there will be a signal which is very high energy on that noise level. So all these are very tough. Current detection method is through matched filtering. What is that? Basically, what people have done is there is now a big theory which is known how gravitational waves are produced. So, if I give them two masses in terms of the solar mass, let us say 15 times the mass of sun and 20 times the mass of sun, and I tell them what will be the gravitational wave, how will it look if these two masses are rotating around each other, then they will give you a waveform. They can calculate. Now, what I can do is, I take that waveform that those people have given me, and I can try to see whether that matches this one. So if, assuming that I have gotten rid of all the noise, so if that matches, then I'll say that this gravitational wave is due to two masses rotating around each other, which are 15 solar masses. One of them is 15 times the mass of sun, the other is 20 times the mass of sun. Now, as you can see, we don't know what is creating. So what we have to do is, that is one filter for 15 times and 20 times two masses. There are thousands of such filters for different masses of those objects. They match them one by one with the gravitational waveform that they are getting. And if one of them matches, then they say that this is the event they have detected. So that is how the gravitational wave is detected right now. A nice name for that is matched filtering, but it is basically matching two patterns, one theoretically calculated and one that they are getting. Most probably within few years, this will be replaced by machine learning techniques. So we'll come to that, what we can do about that. Okay, so that part is over now, how we detect gravitational waves. But I really want you to understand what is going on really. Who are creating these gravitational waves, why they are creating the gravitational waves. So I'll give you a kind of short introduction to astrophysics. In particular, one part of astrophysics that is related to stellar evolution. That means how the stars are born, how they evolve over time, how they die. In particular, we are interested mostly in the death of a star. Not Bollywood stars, but real stars. Okay, I start that by showing you this picture I have taken from Encyclopedia Britannica. It shows that astrophysics or astronomy is a huge area of science. Basically, the frequency of electromagnetic waves can be partitioned into different parts. And this is the part we have television and radio waves and all our mobile phone signals that we use every day for connecting to others. Everything is here. Now, here is a narrow part which is visible light. And astronomy first started by analyzing visible light, by building telescopes that can see the stars and analyze their light. If you are studying physics, you know spectroscopy, because by breaking down light, we can understand a lot about the source of the light or the light passing through some objects between the source and us. So all of those are done in this range. We have red, yellow, orange, green, violet, indigo, blue. There was something we used to remember in school to remember this. Now, below that, there is another kind of astrophysics, which is infrared. Every object that we cannot see through visible light, we can see through the heat that object emits. There are now infrared cameras. If I put here, you will see a lot of heat coming out of all of you. because all of you have some body temperature and that creates heat. Similarly, stars also radiate in infrared. So a lot of people work on infrared astronomy. Then there is a very big area which is called microwave astronomy. Most of the telescopes in this world are actually not optical telescopes, but they are radio telescopes. That means they are specialized in detecting radio waves from faraway sources. One of the most important part of astronomy, for example, in the microwave range, there is a special line from hydrogen atom. Since most of the universe is built out of hydrogen, there is a 21 centimeter emission line from neutral hydrogen atom that is very important for astrophysics. Through that, we learn a lot about the universe. Then there are X-rays, which are much higher frequency. In fact, one of the problems with X-rays is that if the X-ray is coming from a faraway star or something like a star, then it is so energetic that while coming through the atmosphere, it interacts with the gas particles which are in our atmosphere and get scattered. That means get diffused. So if you want an X-ray telescope, it has to be in the orbit of the Earth, outside the Earth. And in fact, there is a very successful X-ray telescope, the Chandra X-ray telescope, named after Subramanian Chandrasekhar, the famous astrophysicist. We'll come back to Chandrasekhar later again. And the most energetic electromagnetic radiation in the universe is gamma rays. We have in India a very nice gamma ray telescope in Ladakh, in Kashmir, or Ladakh is a separate state or whatever right now. So gamma rays are the most energetic in the electromagnetic spectrum. If you go down, X-rays, ultraviolet light, normal light, infrared, microwave, then more or less it stops here. So you can see astronomy is so vast. There are different telescopes for different parts of the electromagnetic spectrum. And most of the time, if we want to understand something about an object, we have to analyze that object in different frequencies. We may have to see radio waves, then we have to see with optical telescopes, possibly with X-rays, etc. So this is very important. And I'll hope that you'll go back and out of curiosity, you will look at all these different kind of astronomy later sometime. Now, that is only the electromagnetic part of the astronomy. Then there are other kinds of astronomy. For example, neutrino astronomy. Due to the reactions that happen inside the stars, a particle which has a tiny amount of mass, but which doesn't interact with anything, called neutrino, that are produced in large numbers. In fact, by detecting and analyzing neutrinos, we can learn a lot about the stars. Then there is cosmic ray astronomy. Very high energy particles are always coming towards us from deep space. And by analyzing those particles, we can understand a lot about the sources of those particles, what kind of processes are generating those particles, etc. And those are also very interesting. And now we have gravitational wave astronomy. It is not a telescope in the normal sense. We don't target it towards the sky. We put it down, as we have already seen, and understand something about the universe using that. Okay, so that was an introduction to different parts of astronomy. Now I have to switch topics, and I have to explain to you in brief about the death of stars, because the objects that produce gravitational waves are actually dead stars. So we have to understand how they die, what happens to them when they die. So that area of astrophysics is called stellar evolution. That means evolution of stars. Now, what is a star? If you have thought about it, that the sun, for example, we see every day. Actually, it's not a good idea to see the sun, but we feel the effect of sun every day. So it is a huge amount of gas which is floating in space. It is neither collapsing nor it is getting diffused in the space. So there must be, you know from your studies in science, that there must be some kind of equilibrium. So to put it together or hold it together, there must be some force which is pulling it inside, and that force has to be supported in equal amounts by giving a force outwards. So a star is actually equilibrium between inward gravitational pull and an outward radiation pressure. Now the question is, we know gravity, that if we put a lot of things, a huge amount of gas in some place, the gas will have a gravitational pull towards the center, but what is producing the outward pressure? The outward pressure actually is produced due to nuclear fusion. So when a star starts forming from the gas in interstellar medium, then when it contracts due to gravity more and more, the temperature inside the gas increases more and more. And there is a point when the temperature is so high that that temperature can fuse two hydrogen atoms and create a helium atom. Now, I don't know whether you have studied some nuclear physics, but whenever two hydrogen atoms are fused into a helium atom, a little bit or tiny amount of mass is lost. And that tiny amount of mass is converted into energy by Einstein's famous equation, E equal to mc square. So that is nuclear fusion. Whenever there is nuclear fusion that starts inside a star, the fusion creates a huge amount of energy that pushes outside. And that counteracts or that balances the pull of gravity. So when the star is forming, due to gravity, it wants to go towards the center, and due to nuclear fusion, there is an outward force, and those two, when they are balanced, a star is formed. So that is the idea of creating a star. Now, in a star like our sun, how the stars live their life, or how long they will live at all, it depends on how big they are. Now, the bigger the star, it lives for a very short time. If there are the stars which are very, very small, they live almost for eternity, for trillions of years. Sun is somewhere in between. The lifetime of sun is about 10 billion years. 1 billion is 1,000 million. 1,000 million is 100 crore. So the sun will live for 1,000 crore years. Right now, it is in the middle age, about 450, 500 crore years it has lived. And it will live another 500 crore years. Okay, so what happens in a star like sun? The hydrogen at the center gets fused into helium. Now, another thing you might have studied, I don't know where, but maybe somewhere in theory of material or mechanics, that if, or even thermodynamics, that heat can propagate in three different ways. Conduction, for example, a metal rod, if you put in fire, then the heat comes through the metal rod. Convection, when you are boiling some water, the whole medium is going up and down. And radiation, where there is no movement of the material, but the heat or the energy flows through space. Now, in sun, all the energy transfer is due to radiation. There is no convection. Sun is so big and the pressure of gravity is so much that the material in the sun doesn't move around very much. They stay together wherever they were during the time when the sun was formed. Now what happens due to that is this. Here you can see the hydrogen at the center of the sun gets fused into helium. Right now it is happening, gets fused into helium more and more. So astronomers call it ash. That means hydrogen has been converted into helium, and sun is not so big that it can burn helium into carbon. So the helium is more and more accumulating, which cannot be fused or which cannot be used for generating energy anymore. Now there will be a time when a very large part of the center of the sun will be filled with helium, but the gravity is pushing inwards. That is, the gravity due to the gas, huge amount of gas, it is pulling inwards. But the helium at the center cannot burn anymore. So what happens is the following: sun's death, red giant. What happens is around the center or the core of sun, there will be a ring-like structure or a spherical cell around the center of the sun, where the hydrogen will burn within a very short time due to the intense pressure of the gravity. And due to that burning, a lot of energy will be produced, and that energy will push the outer part of the sun into outer space. And the sun will grow in size more and more over a very short period of time. That is called a red giant. And when that happens, Earth will be inside the sun. So most probably our fate is that Earth will be consumed by sun at that time. Okay. So that's all good, but we are interested in, even though the outer part of sun has blown away, the core of the sun is still remaining, and there is an intense gravitational pressure which is squeezing that inside of the sun. What happens there? That is called a white dwarf. Actually, this is the true death of sun. What happens is, when there is intense gravity that continues to compress the core, the electrons are stripped off the atoms. So the helium atom that accumulated at the core, all the electrons will be squeezed out due to the intense pressure of gravity. But electron is a particle. If you have studied quantum mechanics, you will know that they are fermions. That means they follow Pauli's exclusion principle. If you collect a lot of electrons within a very short volume, then no more than 2 electrons can be in the same energy level. So what happens then? We have trillions and gazillions of electrons inside that core of sun, and each of them are in different energy levels. So there will be a lot of electrons with a lot of energy. And that energy will now prevent the gravitational pull again. So that is the fate of a star like sun, and eventually it will die as a white dwarf. It will not radiate much. It will float around for eternity in the cosmos. So this thing is called electron degeneracy pressure. Actually, if you have heard of Subramaniam Chandrasekhar, he calculated first what should be the size of a star that can remain a white dwarf due to electron degeneracy pressure in 1918. Okay, so what happens for stars which are bigger than that? This is called the Chandrasekhar limit, 1.44 solar mass. That means 1.44 times the sun, mass of sun. If the core is larger than that, then the electron degeneracy pressure is not enough to prevent gravity from squeezing it further. And if it gets squeezed further for larger stars, then the electrons and protons, they combine and neutrons are formed. So the whole star becomes a collection of neutrons. But now, neutrons are also fermions. So neutrons also follow Pauli's exclusion principle. So now, exactly in the same way, there will be a neutron degeneracy pressure. In other words, the pull of gravity will be prevented again. So that is called a neutron star. We know many neutron stars now through different means. But the main point here is that there are some stars whose depth or whose final, whatever you call it, destiny is a neutron star. But it doesn't stop there. If the star or the core is larger than that, or due to the initial size of the star, then the core, even neutron degeneracy pressure, cannot prevent the collapse of the core. So eventually, the core of the star disappears into a black hole. A black hole is like a mathematical singularity. Nothing escapes it. Well, actually, black holes evaporate. If you keep track of a lot of things, then you know that that is the theory of Stephen Hawking, evaporation of black holes. But for our purpose, black holes are something which is very massive and which doesn't know, nothing can come out of it, not even light. Now, what is the size of these things? A white dwarf can be pretty large. For example, when our sun becomes a white dwarf, it will be the size of current Earth, which is surprising because Earth and sun, they are so different in size that the sun will become eventually that size is surprising. But neutron stars are still smaller. They are incredibly heavy, and the diameter of a typical neutron star is about 14 kilometers from here to, I don't know, Kolaghat maybe. So an entire mass of the star is squeezed inside a ball which is only 14 kilometer diameter. So these are the objects. Now why did I say all this? Because these are the objects which are emitting gravitational waves. Let's see how that happens. Now, we know that most stars in our galaxy, or for that matter in other galaxies, they are created as binary stars. In fact, some people now suspect that Sun was not a single star in the beginning. There was another star which was revolving around the Sun. They were binary companions, and for some reason that star has gone away. But we don't have enough evidence. But astronomers now know that over 70% of the stars in the galaxy, they are binary stars. Now imagine if two stars in a binary system, both of them become neutron stars. They're very large initially. Both of them become neutron stars, or both of them become black holes, or one becomes a black hole and one becomes a neutron star, and they rotate around each other. Now, this rotation is not enough to produce significant amount of gravitational wave that we can detect on Earth. There is one other condition, and that is called quadrupole moment. If you have studied electromagnetism, then you know that a dipole, electric dipole, if it is accelerated, it produces electromagnetic wave. For example, if you take a rod and two balls at two ends of the rod, and make it a positive charge and a negative charge, and then you rotate the whole thing very fast, it will produce electromagnetic wave. Now, with gravity, the problem is there is only one kind of mass. There is no positive mass and negative mass. I'll not do the mathematics as I promised, but it can be shown that gravitational waves are produced due to quadruple moments of rotating massive objects around each other. So, in simple terms, how can there be a quadruple moment? The condition is when the two masses which are rotating around each other, at the same time they are coming closer and closer. So they are rotating very fast and coming close. Eventually they combine and form a single object. So they are called, in gravitational wave astronomy, they are called coalescing binaries. This is the technical term for them. So what is happening then? What is happening is all the gravitational waves that we detect right now, they are created by massive objects which are either neutron stars both, or one black hole, one neutron star, or both black holes, rotating around each other at the same time, coming closer and closer, and eventually merging. So if you remember a picture I showed you long time ago, this picture here, this place is where they are merging, and this place is where they are rapidly coming towards each other. Now, what is the time frame? This time frame is actually a few seconds. That means when they are, we can only detect them when they have come already very close, they are rotating at furious speed around each other and coming very fast, very close, and eventually merging here. And we have only about few seconds to detect them at that stage. As I was telling, that astronomy is many times you want to observe the same object through different types of telescopes or through different types of either electromagnetic or gravitational wave or neutrino, etc. So astronomers call it multi-messenger astronomy. It's important to observe the same object using different astronomical techniques to understand the object better. One of the problems is that the merger of two black holes I'll not say more, but the merger of a black hole with a neutron star or two neutron stars, as you have seen already, the effect or the signals that we can detect is very, very small time frame. That means maybe 10 seconds, 20 seconds, etc. Now, what astronomers want to do is, as soon as that signal is arrived, they want to point their other telescopes, either optical or radio telescopes, at the same place from where it is coming, so that they can measure other effects that may be happening from that merger. So if we detect gravitational wave, we want to observe it in electromagnetic range if possible. One funny thing about gravitational wave that I haven't talked about or mentioned earlier is that when you are seeing light from a source, you are actually measuring the energy of that source, the energy that is coming out as light. When you are measuring gravitational wave, it is the amplitude that you are measuring, because gravitational wave is nothing but ripples in space-time, and that ripple is nothing but amplitude of the gravitational wave. Now, all of you know that the intensity of electric field or gravitational field in Newton's mechanics, it drops by 1 over r square, but the amplitude drops 1 over r. So that means that even if the source is very far away and the strength of the gravitational wave is very, very low, still we get something, because the amplitude decays much slower than the intensity. Now, our work is, okay, another point I should mention, that if I today detect a gravitational wave using my Michelson interferometer, I am seeing that there is a contraction of space-time, and I know there is an event that is happening, maybe two neutron stars are merging, but I have no idea where they are. Where, by that I mean which part of the sky. Now, if I have to tell my friends who are radio astronomers that observe this particular event, then I have to tell them which part of the sky that event is happening. So that is not possible in gravitational wave detector directly. I can only say it is happening, but I don't know where it is happening. So our work is for that. We want to localize where the gravitational wave is being produced, so that if we can quickly localize that, I can tell the radio astronomers that it's happening at least in some small part of the sky. Radio astronomers are very good in sweeping the sky, not sweeping with a broom, but sweeping with a telescope. So they can move the telescope quickly in that region of the sky and zoom into something that is happening interesting. So that's what we wanted to do. We wanted to tell them that where is the source of the gravitational wave. So I don't assume that you have any background in machine learning. So I have some simple examples through which I will explain what we did actually. Now, machine learning is an approach where you give a computer lots of examples and expect the computer or a model, most of the time that model is a neural network model, to learn some pattern out of all those examples. So that when I give an unknown event to the same model, it can predict which particular category that unknown event is. So what we did is, we used machine learning to localize gravitational wave faster and with better accuracy. The method is, we model the sky as a sphere and divide it into many sectors with two coordinates, solid angles actually. We can divide the sky into many different solid angles or sectors. And then we use an artificial neural network to classify gravitational wave signals to one of those sectors. So our aim is to tell the radio astronomers that, okay, right now this gravitational wave is being detected and this is coming from this sector of the sky. We cannot say point. Actually, if you have thought about it ever, there is no meaning of a point in the sky. Because as you look at the sky in more higher and higher resolution, a point soon becomes bigger. You take a point from there, if you increase the resolution, it becomes still bigger, and so on. So we want to tell a region of the sky where from it is coming. So I'll show you some pictures. This is a picture I have taken from an IBM database of faces. Suppose I have lots of pictures of people, and I want to put a video camera, and I want to automatically detect whether someone who is a male is going through this door or that person is a female. So this is called, in computer science, this is called a classification problem. So I want to build an automatic system that will tell me the person right now entering is a male or the person right now entering is a female. The way we do is, these are all examples. I give all these examples to the computer. Simply what I can do is, I can give the entire image. All of you click selfies, so you know that eventually a digital image is stored as a two-dimensional array of pixels. tiny pixels. So each image here is a lots of pixels, and I give this thousands and millions of pixels to the computer and tell this is a male. Similarly, I give this one, I say it is a female, and so on, for millions of such faces. Then the model will learn something that which you don't know, which we will not talk about, but it will try to learn some way that this kind of properties of the image corresponds to a male. Actually, the computer is not understanding anything about what is male or what is female. Everything is a number. I can say a male is a 0. I give this image to the computer and give the value 0 as this one. Similarly, I give this image to the computer and give the value 1. And that way I train a model. So that is the approach of machine learning. In computer science, we call it supervised learning. Why supervised? Because we give lots of examples to a neural network. I'll show you a picture of a neural network soon. And I give a label for each example. The label male and female, for example. So that's the simplest classification task, where there are only two classes, male or female, 0 or 1. Now, there are two classes here, and the neural network is trained with these examples, and this is called the training set. Now, a neural network learns the better when it gets lots of examples. So, for example, if I give millions of faces, its accuracy of predicting the person who is entering through the door, and there is an image of that person which is given to this model, the accuracy will improve as we give more and more examples. In simple terms, you can think of that it has seen all sorts of faces through those examples. And the person who is walking through must have some face which is closer to one of those example faces. So that is one way of looking at it. Now, there are many, many different types of neural network. Some neural networks are good at extracting what we call features. For example, there is a very popular neural network which can tell you if you know there are different types of ethnicity of people. Some people are Caucasian, that means their skin is white. Some people are Indian, some people are Mongoloids, some people are Africans, and so on. So that neural network, if you give these example faces, it will not work so well. Instead, if you give specific features of those faces, for example, people who are Mongoloids from China, Japan, Korea, etc., the distance between their eyes is different from people who are from India. The width of the nose is different from people in India in general. So instead of giving the whole face, I can give some features like distance between the two eyes, length of the face, the entire length of the face, the distance from the nose to the lip. So these things will be specific for one group of people compared to another group of people. Then when I'm asking a question to the neural network, what I do is I want to know whether this person is Caucasian or Mongoloid or Indian. I'll give those features and ask the neural network, give me the answer as 1, 2, 3, or 4, assuming there are 4 classes. So sometimes it is good to give the features explicitly. Sometimes it is good for the neural network to find the features on its own. There are hundreds of different types of neural networks. So what we did, this is a picture of a simplest of neural network. This is called the input layer. If you are giving an entire image as input, there will be 1 million nodes in the input layer. Because each pixel will go to one of those nodes. And there are two nodes at the output layer, male or female. Here it is sector X or sector Y with respect to gravitational waves. And in between there are these layers which are called hidden layers. Now I cannot go into the theory of neural networks, how the training works. Basically neural networks do what is called nonlinear optimization. So the whole purpose of the training is to work out some weights for these nodes so that most of the training samples can be accurately predicted correctly, accurately or correctly predicted. So how you decide how many layers, how you decide what kind of features, those are all black art. There is no science there. You go on experimenting, you try with different features, you find out the accuracy, you try again with other features. If the accuracy improves, then your second set of features is better than the first set. So we did a lot of experimentation. The face recognition, even though it sounds very funny, but the face recognition problem is very similar to our gravitational wave localization problem. How? Because Lynching gave me this picture, but I cannot go into this. Basically, you remember the first slide I mentioned? Let us say only the LIGO detectors, the Hanford and Livingstone. There are two detectors in the United States. Now, if there is a gravitational wave coming, there will be a time lag between the detection at Livingstone and Hanford, because simply one is in Washington, another is in Louisiana. There are thousands of kilometers or thousands of miles in between them. So the typical time lag is about 10 milliseconds. Not only that, there will be a phase difference. If you know physical optics, you know what is phase. Basically, the angle at which the waves go up and down, there will be phase difference between them. So we use these features. To train the model, we use the time lag between the signals, the phase lag, something called a Hilbert transform. There is some maths here. I don't want you to look at or understand this. But what I am saying is similar to the features for face recognition, where I use the distance between the two eyes, width of the nose, distance from the nose to the lip, etc. Here I use other kind of features based on the signals here. Now, how do I generate the training samples? Because as you know, for the face recognition problem, I had millions of faces. Here also, I have millions of fake gravitational waves. How do I know? What I do is, because the theory of gravitational wave, how to calculate from quadrupole moment, everything is known. I simply place a fake gravitational wave source with two masses in some part of the sky, and I know then what should be the waveform in the Hanford detector and in the Livingstone detector. So that way, just like the face recognition problem, I can give thousands and thousands of examples. In fact, in our model, we gave about 1 lakh or 100,000 examples by creating fake gravitational wave signals. Now, there is another thing here. We can do that in electromagnetic astronomy. We cannot do this because in radio astronomy or optical astronomy, when there is a source of the radiation, we don't know what is in between. There may be dust, there may be a hydrogen cloud or something like that, which may reduce the intensity of the electromagnetic radiation. But nothing can prevent a gravitational wave from propagating, because it is the ripple in space-time. So this is the way we set up. Basically, we generate lots of samples. We have Python programs. I think all of you learn Python. So we have Python programs which we run for hundreds of thousands of times for generating fake gravitational wave samples for Hanford and Livingstone detectors. Then for each such sample, we extract those features and we input those features to a neural network and train the neural network that way. And then we give the neural network an unknown gravitational wave sample, and it predicts, because it learned somehow that if the signal comes from this part of the sky, there are some patterns in this symbol between the features I am supplying it. If it comes from that part of the sky, there is a different pattern. So it learns those patterns, and then it predicts very accurately where in the sky it is coming from. So that is our work. These are all feature detection. I don't want to go into all the details of the features. So we did some experiments separately. For example, for pure signals, as I told you earlier, that one of our real trouble is that the signal is never pure. There is a lot of noise in the signal. For pure signals, we can achieve very high accuracy for predicting the sector from where the gravitational wave is coming. For signal with noise, we can't achieve that far. Still, we achieve about 92% accuracy for 2048 sectors. Actually, this accuracy drops a bit when there are more sectors. But then still, it is better than what is known. So if you look at this as the sky, we predict like this. So according to our neural network model, it says the gravitational wave is somewhere here. Now, somewhere here is not perfect, but as I told you, that radio astronomers can quickly scan through that part of the sky and see whether there is something in the electromagnetic spectrum that corresponds to that particular gravitational wave source. And we can do it very fast. Actually, training the neural network takes long time. But once it is trained, we can do the prediction in milliseconds compared to what is done now in LIGO. So right now we are trying to put this in the LIGO, they call it pipeline. So we are doing more experiments with different kinds of noise, and eventually this will go into the LIGO pipeline so that not only the gravitational wave will be detected, but its source also will be localized in real time, immediately. So that is our aim. So these are the future works we are doing. Our model is not very good for low mass, low mass black hole, binary black hole. BBH is binary black hole. Actually, our model is working very well for black hole merger. If there is a black hole merger, then we can predict with close to 100% accuracy. Unfortunately, black hole mergers don't produce any electromagnetic signature. So if we want to make it useful, we have to eventually do it for neutron star, and neutron star black hole mergers. So we have a lot of work to do for improving the model. So I'll stop there.
Okay.